My sound is clear, I think so. Hello. Okay. So, very good morning to all of you. Myself, Professor Navidakar Mirza from Maulana Mukhtar and Ahmedabad Technical Campus. So, due to shortage of time and I am not available for 15 days in a month, so we have to complete the syllabus by taking extra classes. So today is also the extra class, and tomorrow my third year summation. That's why also our class might be not possible, but I will try to take the first lecture if possible, and because from second lecture onwards I will take submissions for the higher classes. So today we will see, previously we have seen the Moody's diagram and velocity distribution uh, by using the Gauss-Weisbach equation of head losses. And in energy losses we have seen there's a major and minor losses. The major losses is due to the friction and between the movement of the fluid and due to the viscosity, and minor losses due to entry of the pipe, exit of the pipe, sudden expansion and sudden contraction of the pipe we have seen, and some of the losses due to the friction loss, and that friction loss is considered to be a major loss. So we will start at the Darcy-Weisbach equation of head loss. Given major loss of head in a pipeline, whereas loss of head due to changes in pipe section, bends, fittings, walls, etc. constitute what are called as the minor losses of head. Okay, so we will already seen this. Okay, the major losses is due to the friction loss, and minor losses is due to the bend and change in cross section, change in the cross section, and exit or entry to the system. Okay, so this major loss in terms of friction factor we find out with the Darcy-Weisbach equation, that is FL V square upon 2G capital D. And minor losses, there are many minor losses which are depend on the length of the pipe and diameter of the pipe, etc. They are nothing but entry to the pipe, loss due to entry to the pipe, exit to the pipe, sudden expansion of pipe, and sudden contraction of pipe. Okay, suddenly the change in diameter of the pipe is nothing but if smaller diameter change in the larger diameter, so it is nothing but sudden expansion, and if from the larger diameter to the smaller diameter, we can see that is a constant contraction. It is due to the contraction to the pipe, and it is due to the expansion of the pipe. Okay, pipe from smaller diameter, let's say D1, D2, and it is D3. So from D1 is smaller, D2 is larger, it is sudden expansion case, and here at entry of the pipe there is loss, and exit of the pipe there is loss, and between the pipes there is the friction losses, what we are say that HF. Okay, so HF we are seeing the friction losses into the pipe. Okay, so these are the losses, major and the minor losses into the pipe. We know that the equation for the Darcy-Weisbach friction loss, that is HF is equal to, we find out FNV square, FNV square upon D into 2G. I will say this one is the equation number 1. And most useful equation in solving fast flow problem is nothing but your Bernoulli's equation. Okay, the most useful equation in solving pipe flow pipe flow problem 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 is Bernoulli's equation. And you know the Bernoulli's equation? Many times we have equation, or we can say the Bernoulli's theorem. Okay? Bernoulli's theorem. And it is, you know that Z, that is bottom head plus P upon gamma pressure head plus kinetic energy head, that is V square upon 2Q is equal to constant, that is nothing but your Bernoulli's theorem. Okay, so it is to be applied to a specific point. If you are applied it into the two specific point at the pipe, if this is your pipe, and if you apply the Bernoulli's theorem at two sections of the pipe having a length of L. Okay, so that is L distance apart, one pipeline, then it can be written as, Z1 plus P1 gamma plus V1 square by 2 is equal to Z2 plus P2 gamma 2 upon gamma plus V1 square, V2 square upon 2G plus, that is HF between 1 and 2, or is between 1 and 2, it is the distance apart L, so you can write down this is H head loss HFL. Okay, you can write it like this, or you can write this also HF between 1 and 2. Okay, so this is the major HF 1 and 2, this HF plus section between the 1 and 2. It is nothing but this equation of Darcy-Weisbach equation of 2G into D. There is major head loss due to friction. It can be said that a major loss of head due to friction caused by friction caused by the flow of liquid over a pipe length of that is capital. We are denoting it with the capital. Okay. Here the F is nothing but the friction factor. F is nothing but the friction factor. And also we have seen that this F is not specified, can be taken in between, the value of it can be taken in between 0.015 to 0.02, and preferably is taken as 0.02. Preferably it is taken as 0.02. But in case of if friction coefficient is given, friction वेक्टर की जगह अगर क्वेश्चन कोएफिशिएंट एफ डैश दिया हुआ है तो वी आर यूजिंग द फार्मूला you know that f is equal to 4 times of f dash. I think so. So f dash is equal to f of by 4, or you may write that 0.25 of f. So you can write down this formula for the head loss between the pipe flow section 1 and 2. The 4f dash LV square upon 2g into b. Okay, and the f dash value, remember it is 0.005. And Reynolds number is the most important number for pipe flow system, and it's calculated by. So Reynolds number proves the flow pattern. So it is very important. Differentiate between the laminar transition and turbulent flow. That is rho VD upon mu. This already we have seen in previous units also. The Reynolds number. Okay, it depends on the your inertia force and the viscous force around number. Okay, and head losses on account of sudden contraction, sudden expansion into the pipe, with the pipe bends and fittings. These are the major losses we have already seen. Here, bends and fittings into the pipe, that is bends है, elbow है, T है, हम join करते हैं, and nozzles due to the minor losses are there. So this is the already major loss we have seen the in previous lectures. That is the series sec equation for the head loss. And now we will see today the sudden expansion and sudden construction of the pipe, the losses, that is minor losses. So we will see, and then another losses we will from this derivation we can come for the another losses. So first we will go for the student, they are joining there. If I miss your attendance, that you don't mind because you are disturbing the class. So we will see first the loss, minor losses, loss on on account of account of sudden expansion, sudden expansion, sudden expansion. Okay. So for that we have to draw the figure. So draw the figure first and draw with me. Okay. So you can draw the figure. So draw this figure. The smaller pipe, the flow through the smaller pipe. Okay. And suddenly what happened? Suddenly what happened? Your change in dimension of the pipe is occur. The smaller pipe merges with the larger pipe. Smaller pipe it is merges with the larger. Okay. This is your pipe. Hmm? Smaller diameter pipe and it merges with the larger diameter pipe. Okay. So you have to draw this figure. Please draw carefully. And the discharge through the pipe diameter, I will say this smaller diameter pipe D1. Okay. Large diameter pipe, I will write down, that is D2, capital D2, capital D2, depend on you. You may write small or capital, depend on you. And I will take the three sections here. Section 1 at smaller diameter pipe. Section 1 at smaller diameter pipe. Okay. And one other section I will take where the vortex is formation. I will not order. And then another section I will take that the change in the diameter, that is smaller to larger diameter of pipe, and I will say that this section 2. So this one is section 1 and this one is section 2. Okay, the liquid is or fluid is flowing from the discharge tube. Okay, because the pipe in series, therefore discharge will not be changed. Okay, and in the first phase. Okay, so I will write down this is moving with the velocity v1. Okay, then again continues the discharge q. Okay, the discharge q exit to the pipe. You can write down and having the velocity v2 in the pipe 2 in the this. So this is the flow through the pipe. Here I will draw also this liquid flowing through the pipe. And then due to the sudden expansion, what happened? The, the flow also expands, okay, till it reaches to the section 2. This is the flow. Okay, so this because right. Draw this merges with the same diameter of the pipe 2 at section 2 will also be broken. Okay, so gradually it reaches to the diameter, the flow reaches to the diameter of the pipe. Huh? It adjusted itself to the diameter of pipe, and if the vortex or radius formation due to this sudden expansion of the pipe. Okay, so this is sections, and if you measure the head, you can see the pressure head here, pressure head here, and pressure head at section 2. Okay, so the level maybe at the start it will be here, then it will slightly increase here, and here also due to the enlargement of section it will increase here. So I will dash this level of the pressure level of the pipes with the bottom. Okay, so this from the center of the pipe, this one, the pressure head P1 upon gamma, and here from the bottom you can write down from here to here it is P2 upon gamma, that's pressure head, and then if you draw the diagram, it will be like this, and it changes. Okay, and the control volume I will write down this from A, section A, then B, C. Here diameter is changing here. Okay, diameter is changing A, B, C, and then here I will write on this D, D. Or better I will change the color. Okay, understand. A, A, B, C, D, and here I will say it is E, F, G, and H. So this is control volume, and this figure is very important. This figure you have to draw carefully. I think so. This figure is clear to you. जैसे मैंने बनाया, अगर आपने फॉलो किया होगा अगर में, तो ठीक है. So sudden contraction of the pipe, change in pipe diameter, ठीक है, change in pipe diameter due to sudden expansion, due to sudden expansion, due to sudden expansion. Okay, so it is clear up to you. I think so. Now you can see here. Uh, you can consider a pipe. I will not write the description. Description you will get in my notes. So here you can see the consider a pipe of diameter d1 has to get enlarged suddenly to the diameter pipe d2. Okay. Then at entry into the large pipe, we find that loss of turbulence and ADS formation coupled with the loss of energy. Yeah, due to sudden expansion of pipe. This is mainly due to separation of streamline from the boundary as the velocity in larger pipe for same discharge through smaller larger pipe will be lower. So velocity will be reduced from the smaller pipe to the when it converted to the larger pipe. The velocity will not be same. Okay. But the pipe is due to horizontal. The pipe is horizontal. Therefore, the datum is same. Datum is same. That is Z value will not be considered in the Bernoulli's theorem. So this will be clear from the application of Bernoulli's theorem between section 1 and 2 as shown in the figure this one. So if I write down the head this Bernoulli's equation for this sudden expansion P1 plus P1 is square upon 2G because Z is same. तो Z अगर अगर आप लिखते भी हैं तो P2 upon gamma plus V2 square upon 2G and plus this loss of it. So this Z will not be there. It is same due to the horizontal line. So no need of writing this. Okay, as in the case of Bernoulli's equation, we are writing. So datum is same and the datum head Z is same as pipeline is horizontal and HL is the loss due to sudden enlargement. So this is HL here and loss due to HL is due to sudden 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 expansion into the pipe diameter. Sudden expansion into the pipe diameter. Now applying the momentum principle, applying applying the momentum principle, only momentum principle, you know, M into V, M1 V1 is equal to M2 V2. That is the momentum principle. Okay, that is the momentum principle. To the control volume, control volume, control volume. We are considering from A, B, C, D, E, F, G, H. Okay. This is the control volume from the with this equation you can see from A, B, C, D, E, F, F, G, H. This is the control volume. Okay, we are considering for the study and assuming that assuming and assuming that assuming that the annular 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 space CD, CD and GF here's the equation that rho into Q into V2 minus P1 is equal to P1 A1 plus P1 into A1 minus A2, the change in the diameter. So larger diameter A2 and smaller is A1. So A2 minus A1 minus P2 A2 minus P2 A2. Okay. So if we write down this P1 A1 plus P1 A2 minus P1 A2 A1 or A1 A2 minus P2 A2. Okay. So P1 A2 minus P1 A1. P1 A1. Okay. P1 A1. Minus plus this will be cancelled. So it will be P1 minus P2 into bracket. This is A2. So if I will write down the term in terms of the pressure head, that is P1 minus P2, change the pressure head, section 1 and 2. So this A1 will become here rho into Q by A2 in bracket P2 minus V1. Okay. Now again, as we know, as we know, as we know, as we know, average velocity, average velocity V2 is equal to Q upon A2. Q upon A2. So I will write down the P1 minus P2 is equal to rho into V2, V2 minus V1. Okay. So if you write down the HL, the head loss due to the sudden expansion, if you write down the P1 minus P2, P1 minus P2 upon gamma plus P1 square minus P2 square upon 2G. Okay. This equation from equation number 3. From equation 3, earlier we have written here. Here it is on equation from this equation. From the equation you can, in terms of HL, if you write down P1 minus P2 gamma plus P1 square minus P2 square upon 2. Okay. So likewise it is just written here the same equation in terms of HL. Now we know the P1 minus P2 value. You can put the P1 minus P2 value. We have just calculated, that is rho into V2, V2 minus V1 upon gamma. And you know gamma is nothing but rho into G. Rho into G. So I will write down here is rho into G. Okay. Rho into G plus V1 square minus V2 square upon 2G. Now this rho will be cancelled. So I will take the common 2G. 2G value I will take the common. So here G is there, to 1 multiply by 1. This value will multiply by 1 and this will multiply by 2G. So it will be, if you write down, if you have taken the 2G common, so it will be multiplied by 2. So 2 V2 square minus 2 V2 V1, okay, plus V1 square minus V2 square. Okay. So these two terms are having same. So 2 V2 square minus V2 square is nothing but V2 square. I will write down V2 square minus 2V2 V1 plus V1 square upon 2G. Okay. Now you know this mathematical term. Huh? If you expand V2, I will just show for mathematics, then you can understand that A minus B, A minus B whole square. So what will we do? A square minus 2AB plus B square. है ना? This is the mathematics. So applying this law, rule of mathematics, what we will get? That V2 minus V1 whole square is equal to V2 square minus 2V2 V1 plus V1 square. Okay? Or you can write in vice versa. You can write in vice versa also. V1 minus V2 square also. The same value will become. Write on V1 minus V2 square. It will be also the same V1 square minus 2V2 V1 plus V2 square. Either you write this or this term, no issue. Okay, but the higher value will be written first. So you can write down this HL is equal to V1 minus V2 whole square upon 2G. This is our equation number 4 if I will give you. Okay, this mathematical terms you should know. So if I will write on here, so you should understand that this is the higher velocity minus lower velocity whole square on 2G is nothing but head loss due to. Now we know that uh, for continuity equation, for continuity equation of the control volume, you can say. So you know that A1 V1 is equal to A2 V2 because discharge is constant in the pipe in the series. Okay, so you can write down like this. If you put the in terms of V1 only, for your HL in terms of V1, V1 square upon 2G, it will be 1 minus A1 upon A2, the bracket square. Or you can write in terms of V2, so it will be HL is equal to V2 square upon 2G, but here what it will be reverse, A2 upon A1 minus 1 whole square. Okay, so any of the term you can say it is the equation number 5. Equation number 5. So head loss due to sudden enlargement is given by head loss, head loss due to sudden expand, expansion or enlargement of pipe of pipe given by given by equation equation 4 or equation 5. So this is nothing but of loss of head due to sudden expansion, and this was first developed by this the above Loss equation, loss equation. First was first obtained by first obtained by the scientists Boda and Carnot. Boda and Carnot. That's why this equation is it is also known as and hence and hence it is known as it is known as is known as Boda Cornet equation. Head loss equation. Okay, so this is nothing but due to the sudden uh, expansion of the pipe. Now, if you see that this is the due to the sudden expansion, and exactly the opposite case what happened if there is opposite case that the pipe is large and then diameter of pipe is reducing. So that is called as sudden contraction. That is called as sudden contraction. So in sudden contraction, what happened? This is the pipe having diameter, large diameter, okay, and then sudden the pipe reduces. So this is the case of sudden contraction. So if you write make a figure, so this is a case of so you can write on loss due to sudden contraction of the pipe. Sudden contraction of the pipe. But it can be written as it is not subluxation or expansion due to the some. You can see this figure. If here also I will take the two section 1 and section 2 section 1 and section 2 and you can see that here we will draw a figure. You can see the sudden the flow reduces to the smaller diameter pipe. The flow from large diameter of pipe it reduces to the smaller diameter of pipe. What happens? It will make some contraction more and then it will slowly merge with the diameter and continue to. Okay. So at section 2 when reaches it, then uh, it will be. So I will write down here. So this here the formation of vena contracta is contraction of this flow at this level. It is called as vena contracta. So I will again make one section where the contraction of the flow will takes place, and this section is C. And this section is C here the vena contracta. So it is called as here the area is AC and it is nothing but area at the contraction of the flow. It is called as vena contracta. Area at vena contracta. Okay, and this area is nothing but CC into AC A2. because it merges with the area A2. This is diameter D2, and so area A2, and this is diameter D1 for the larger pipe. Okay, so here it is area A1, and here area it is area A2, and AC is the area at Vena contractor. So if you see that here, what happened? The flow from the larger pipe, it converged to the flow in the smaller diameter of pipe, and due to that there is some formation of this flow here. Contraction of the flow takes place, and the velocity in the this flow, it is different. It is V1, so here it is V2. Discharge is same as it is, nothing but the Q enter to the pipe and exit to the pipe. It is also Q because now some of the head losses is there. Okay. When flow from larger diameter pipe takes place into smaller diameter pipe, the loss of head is known as loss due to sudden contraction. The fluid entering into a smaller diameter pipe will have it into its streamlines converge up to vena contracta and then expand gradually till fully established flow at section 2 takes place. Thus, this is actually a case of sudden expansion between section C and section 2. So, it is nothing but the case of sudden expansion, sudden expansion between section C at vena contracta and section 2, that is the smaller diameter pipe. So it is a sudden contraction of the pipe, but you can say that it is a case of sudden expansion between the section CC to the section 2. Okay, then head loss we can written as from the above equation we have formed HL you can write down due to construction V2 square upon 2G A2 upon AC equal A1 minus 1, that is whole square. Okay, because as AC is equal to EC into A2, and so you can write down the head loss in terms of CC. So you can write down HL is equal to V2 square upon 2G. So this A2 and CC into A2 minus 1 whole square. This A2 will be cancelled. So our HL will be that loss due to sudden contraction into the pipe is nothing but V2 square about 2G. The diameter of vena contracta you to find out 1 upon CC minus 1 whole square. And here CC will be here. CC will be coefficient of contraction. Coefficient of coefficient of contraction, and its value in generally it is 0.6 generally. The value of CC is generally 0.6. So 1 upon CC minus 1 whole square, it is generally coming as 0.45. Usually it is usually taken as 0.5. 0.5. Thus HL will be, in case of sudden contraction, it is nothing but K times V2 square upon 2G. This will be, I will write down the equation number 6, and K is the minor loss coefficient. K is the minor loss coefficient. Minor loss coefficient. Okay, so this one is the our uh, this, loss of head. Loss of head we have seen due to sudden expansion. Loss of head due to HL due to sudden contraction. This one, and earlier we have find out due to sudden expansion. So derivation you can make like this. Now the other minor losses we will not go for the derivation. We will see that, and then we will go for the hydraulic gradient and energy gradient. Uh, so we will take a short break here for 5 minutes. Are you there? I think so. Don't leave the class. We'll solve one example if possible. Uh, okay. So this, I think so. You are understand this, and then we will see the what is the hydraulic grade line. Already hydraulic gradient and energy gradient. That is total energy line. Also, energy gradient is also called a total energy line, and we will see that what is the hydraulic gradient and energy gradient. So we will take the short break and we will start the second class. तो ये समझ में आया आप लोगों को?